Acoustics is the science that deals with sounds. Film with some of the basic principles of acoustics. Invisible waves of sound behave much like visible waves of water. When water is disturbed, waves form at the center of disturbance. The waves move until they strike an obstacle and are reflected back, or until their energy is dissipated. Sound waves travel in a similar manner. Sound in air travels about 1,100 feet a second. Since light waves move much faster than sound waves, the cause of a sound may be seen before the sound is heard. Reflected sounds are called echoes. Echoes, particularly indoors, are not distinct because the successive reflected waves interfere with the original waves. Upon striking an obstacle, such as a wall, part of the wave's energy changes into heat. Part passes through the obstacle, and part is reflected. The dashed lines represent reflected waves that are nearly dissipated. You have been hearing this explanation under nearly ideal conditions. If the walls of a room are lined with a hard, non-absorbing material, they reflect the sound waves. The sound in a room of this kind is distorted because the reflected waves pass back and forth from wall to wall many times before they are dissipated. If the walls are covered with some thick, porous material, they absorb much of the energy of the sound waves. Sound produced under this condition lacks the live quality that usually characterizes indoor speech. The live quality is lost because there is so little reflection. A curved surface in an auditorium may be detrimental to good room acoustics because it reflects and focuses the sound waves much as a curved mirror reflects and focuses light waves. Here, echoes follow the original sound by an appreciable time interval and interfere with clear reception. Such an obvious structural defect can, of course, be avoided in the construction of a building. Often there are other conditions that affect listening enjoyment. To study some of them, acoustical engineers may use the oscilloscope. This instrument pictures invisible sound waves by translating them into visual patterns. Then the visual patterns can be studied. Here, for example, is the pattern of a group of woodwinds. Musical sounds produce regular patterns. Noises produce irregular patterns. Even at low intensity, noises tend to irritate the listener. Musical sounds tend to be enjoyable. If a study of sound wave patterns reveals undesirable components, steps may be taken to control them. Audible sounds are transmitted to the brain by the ear. Sound waves first reach the outer ear. This is the part of the ear that collects sound waves and directs them to the eardrum. Changes in pressure caused by sound waves affect the eardrum as they would affect any other diaphragm. So the pressure changes caused by longitudinal waves of sound in air or in fluid cause the eardrum to vibrate. Just beyond the eardrum is a cavity called the middle ear. In this part of the ear are the three small bones that transmit vibrations of the eardrum to the inner ear. The inner ear, which is spiral in shape, is filled with fluid. When the bones of the middle ear vibrate, the vibrations are transmitted to this fluid. Within the spiral-shaped inner ear is a membrane in which nerve endings of the auditory nerve are located. Vibrations in the fluid excite these nerve endings and transmit nerve impulses along the auditory nerve to the brain. When the sound wave impulses arrive at the brain, the person experiences the sensation of hearing. The healthy, normal human ear is sensitive to a wide variety of sounds. We can represent the range of human hearing on a graph. Normal hearing ranges in audible intensity or loudness from the faint rustle of leaves, represented by the lowest part of the curve, to the boom of distant artillery, represented at the top. In terms of audible frequency, the average person hears from about 20 cycles to about 16,000 cycles a second. That's considerably more than the range of the piano scale. The range or area of hearing varies between individuals, as shown by the zone between the two outer sets of lines. Modern electrical reproduction approaches the audible frequency limits of the original sound employed. When normal amplification is reduced in volume, hearing is affected. Notice the change of quality in speech caused by this unnatural volume. Eliminating the lower frequencies makes another change in sound. This causes an unnaturalness, particularly in the vowels. Eliminating all frequencies above 3,000 cycles causes another important change. This change in audible frequencies affects the consonants. And finally, here is sound with both high and low frequencies eliminated. This kind of distortion produces a very noticeable effect on musical sounds as well as on speech. In singing, the overtones of the highest note may reach about 7,500 vibrations a second. These sound waves, of course, are audible. The oscilloscope can also reveal sounds that are not audible to our ears. One way to produce inaudible sounds is to use an audio oscillator. First, the dials are turned through the range of audible sound. Now the oscillator is producing a 30,000 cycle sound. We can't hear it, but this is how it looks on the oscilloscope screen. And here's a 50,000 cycle sound. Such frequencies above the range of hearing are supersonic or ultrasonic sounds. Supersonic devices, called sonar, are used to detect objects underwater. Wartime detection may lead to the destruction of enemy submarines. In the air, the supersonic sound barrier has been overcome, so that speeds greater than the speed of sound are now attained. Acoustical research progresses on many fronts. For example, this room, called an anechoic chamber, is constructed to absorb nearly all sound waves. The absorbent materials are packed into cones. In this room, engineers can test the acoustical properties of microphones, loudspeakers, and other equipment with almost no interference from echoes. The results of acoustical research can be applied to all kinds of situations involving sound. Principles of acoustics are of particular significance, for it is through the application of these principles that sounds are transmitted from their sources